Welcome back to 6-1. Today we're continuing the conversation we started in the other notes, but now we're going to dive into the idea of when do radicals not simplify nicely? Okay, so again, I referenced this in the last notes. Square root of 25 is easy. Boom, we just get 5. But remember, when you took the square root of 50, you had a little bit more work to do in terms of simplifying that radical. So that's kind of the investigation we're talking about today. What happens when they can't simplify nicely? So we're going to start by looking at what do we do with numbers, then what do we do with variables, then putting it all together. So the first thing is you want to identify the index of the radical, okay? Because that's going to tell you what column of the powers chart you're going to look at. Again, you've already kind of been exploring this idea, but it is noteworthy that that is your first step. If the radicand is on the list of that column, the number to its left is the answer. Again, you were seeing this yesterday as we were doing our notes. If I was looking at the fourth power list and I wanted to know, oh, what is the fourth root of 81? My answer is that 3. Okay, so that's what that part of the rule means. Then, if your radical isn't on that column, then look for the largest number in the column that divides it, okay? And again, you saw this in terms of square roots back in Expo and even in our chapters 4 and 5 in Algebra 2, we've already been exploring that idea, okay? After you do that, you want to split up the radicand using that number, and you want to simplify by taking the root of the perfect piece that you broke out. Again, these are all things, it probably looks harder than it is when I write it all out in words, but this is a good way for you to go back and reflect if when you're doing your homework, if you start getting confused or frustrated, you can kind of go back and look at that step-by-step process. All right, so let's remind ourselves what all of this looks like, what all of this means, okay? So again, back in Expo and in our chapters 4 and 5, you've already seen things like square root of 75, okay? Square root of 75, well, that is not on our list. So if you were to look at our powers chart, square roots are the second column. I'm not seeing 75 anywhere on that list, okay? But what I am seeing is I'm seeing the number 25, okay? Because the number 25 evenly divides 75. In fact, it splits it up into 25 and 3, right? 25 times 3 gives me 75. So that's what I meant by find the biggest number that will divide the number that is on your list. All right. And now from here, you know the square root of 25. That was on that chart. Square root of 25 breaks free and is just 5, while the square root of 3 is stuck. That piece cannot come out. All right, so again, that's the basics of what we're talking about doing, okay? However, of course, it is going to escalate to become a little bit harder. So let's look at the next one, cube root of 24. So if I look at my powers chart, a cube root is going to be in that third list. And unfortunately, I'm not seeing the number 24 on there. So that means this is not a perfect cube, okay? Not like yesterday. However, I see a number on that list. I see the number 8 that can divide 24, correct? So I'm going to split it up using that idea. So here I'm splitting up the cube root of 24 is the cube root of 8 and the cube root of 3. And the reason that I'm breaking it up that way is because according to my chart here, the cube root of 8 is just going to give me the number 2. So I'm going to break that free and I'm just going to call it what it is, okay? It's just the number 2. And then the cube root of 3 is stuck. It's not going to be able to break free. Now notice I left a little space here, okay? I left a little space because I also have a variable happening here, right? X to the third power. So remember, for variables, I have to ask myself, how many times can 3 go into that exponent of 3? Well, 3 only goes into 3 once, so it's going to pull out as an x to the first. Okay? And because it's an odd root means I never have to worry about that power or that rule, correct? So let's look at our next example. Fourth root of 32. So I'm going to go straight to my powers chart. A fourth root means I'm going to be looking at this column right here. And again, the unfortunate thing is I'm not seeing 32 on that list at all. But I am seeing a number that can divide 32, a number that I can use to split 32 up. All right, so I'm going to use that 16. So I'm going to split up 32 into the fourth root of 16 times the fourth root of 2, because 16 times 2 gives me the 32 that I started with. And if I look at my chart, the fourth root of 16 just gives me the number 2. So that part I'm going to break free. However, the fourth root of 2 is not going to be able to break free, okay? That is going to stay stuck inside the root. And then I start asking myself for the variables, how many times can 4 go into 8? 4 can go into 8 twice, and 4 goes into 12 3 times. Now, because this is an even root, okay, with those variables, now I have to be careful. When you have an even root, now I have to check that rule, that even, odd rule. So for the x, it started with an even power, even root, and then it pulled out as an even, as x squared. So that doesn't need the absolute value, okay? That's not my concern. However, look at the y. The y started with 12, so even, then a fourth root, so that's even, and it pulled out as a y cubed. It pulled out as an odd. So there, even, odd means I need those absolute values there. Okay, so as we're going through this process, we do want to make sure we're recalling when do we need absolute values, when do we not need absolute values. And again, you always remember with that even, odd rule. All right, so that's a little exploration on what to do with numbers that don't break up nicely. Now, if you recall from Expo, there are also times that the variable isn't going to pull out nicely. Okay, so we also have to explore that idea. What do we do when the variable is the not nice part? Okay, if the index doesn't go evenly into the exponent of the variable. So the number times n does go into it, still pulls out just like yesterday, but any leftover piece is going to stay inside the radical. So what do I mean by that? Well, let's take a look. So for x to the 5, okay, so here we're talking about an even root, okay? So we want to see how many times can 2 go into 5. So some of you are going to be able to do that really quickly. Oh, 2 can go into 5 twice with 1 left over. Some of you, that's not going to come as naturally too. So if you need a visual aid for this, if I'm looking at those 5 x's, 1, 2, 3, 4, 5, if I'm looking at those 5 x's, okay, I can use 2 groups of 2, correct? So I can make 2 groups of things that I'm going to be able to pull out. And then I have that one that's left over, okay? And the leftover has to stay inside the root, okay? So that's another way to think of it, is how many times can 2 go into it? Well, some of you will be able to quickly say, oh, 2 goes in twice with the 1 left over. Or some of you will need the visual of, okay, I need to be making groups of 2. How many groups of 2 can I make? All right. So again, just another way that you can think of this. Now this is an even root, so we do have to think about that even, even, odd rule. So let's look at the x. X started odd, then even root, even power. On the outside, well, that doesn't fit the even, even, odd rule, okay? So this one does not need those absolute values. All right, let's take a look at this next one, the cube root of negative 125. So cube root, let's see here. So cube root, I'm going to look at my third column. 125 is actually on my list. So that's just going to give me a 5. However, because it's a negative, it's going to pull out as a negative 5. Because remember, odd roots can have negatives inside the radical. Now, again, we need to think, how many times can 3 go into 7? So again, some of you will know it really quickly. Oh, 3 can go into 7 twice with 1 left over. Some of you will need a visual. 1, 2, 3, 4, 5, 6, 7. So how many times can 3 go into it? So I'm going to make groups of 3 to see how many times it can go into 7. Well, it can go into 7 2 full times with 1 leftover piece. Okay? So again, if you want that visual, it can be very, very handy to you. If you're good mathematically, you can just do it mentally. That is also absolutely fine. Here, this is an odd radical, so the nice thing is I don't have to worry about checking my rule. I know I don't need any absolute values when I'm dealing with odd roots. All right, let's look at our next example. Fourth root of 625. So let's go look at our list. So fourth power, 625. It actually is on our list, so that makes us really happy. And it's going to pop out to just be 5. So here, there is the fourth root of 625. Then 4 goes into 4 exactly once. So that one's going to be nice and easy, right? When it evenly goes into it. But that 10, those y's are going to be a little bit more complicated. So again, maybe you'll be able to see really quickly, oh, 4 goes into 10 twice with 2 left over. Or you might want that visual. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You may want the visual of saying, all right, how many times can 4 go into it? So I'm going to make groups of 4. Oh, okay. 4 goes into it twice, and now I have 2 of them that are left over. All right, so again, whichever way works best for you. If you want the visual, please write it out. Take the time to do that. If you don't need the visual, then you can just say, oh, 4 goes into there twice with 2 left over. Whichever way works best for you is completely fine by me. Now, this is an even root, so I do need to check those variables that I was pulling out. So the x started as an even root, came out as an odd. So the x actually does need absolute value, because if there's no root shown, it means the root is 1, or sorry, if there's no power showing, it means a power of 1, which is odd. Now the y I don't have to worry about, because notice right away, I notice the y pulled out as an even power. Okay, and we're only worried about when they pull out as odd powers. So as you get good at using this rule, sometimes you'll be able to see shortcuts like that, right? That you'll be able to easily identify when it does, or when it is or is not needed. And then remember, typically I like to write things not in the absolute value together and then follow with absolute value, followed by the root, okay? It's not a huge deal. It's just the way that you'll typically see me write it, is I'll group the things that are not a part of the absolute value together, followed by the absolute value, followed by the root, okay? Otherwise, again, not the biggest deal in the world if you forget to switch that order, okay? So let's work on pulling some of this together, okay? So all the ideas we've covered today, let's start working with them. So cube root of negative 54. So unfortunately, when I go and look, third power, because it's a third root, 54 is not on my list, okay? So what we need to do is look at what number on here can divide the 54. And if you notice 27, 27 divides 54, okay? 27 times 2. So I'm going to split up that 54. And I'm going to split it up so that negative is with the part that I know is going to break free, okay? So, and that's that little side note that I have is that the negative always pulls out. Never leave the negative inside the radical. And again, it's appropriate to have that negative because it is an odd power, so it is acceptable. Cube root of negative 27. Well, cube root of 27 is 3, so that's going to give me a negative 3. And then I'm going to leave some space for the variables, okay? So the negative 27 breaks out, the 2 stays stuck inside the radical. Now let's take a look at our variables. So how many times can 3 go into 6? Well, that's one of the nice ones, right? 3 goes into 6 very nicely twice. How many times can 3 go into 8? Now again, this is one, maybe you can do without that visual aid. I'm going to continue to show you that just in case you need it. So 1, 2, 3, 4, 5, 6, 7, 8. How many times can 3 go in there? So I'm going to start making groups of 3. Okay, so I see 2 groups of 3, so that's what comes out. And then there's 2 leftovers. So those 2 leftovers have to stay inside. It's an odd root, so I don't have to worry about that absolute value rule. I know right away it's not going to be necessary. All right, looking at our next one, a fourth root. All right, so fourth root of 48. Let's go check our list. So fourth root, well, again, unfortunately, 48 is not on my list, okay? So that means I need to look for a number that can divide that 48. And thankfully, 16 meets that criteria. 16 times 3 gives me 48. So that's how I'm going to break this up. The fourth root of 16 and the fourth root of 3. And what is the fourth root of 16? Well, according to my chart here, the fourth root of 16 is 2. So this is going to be a 2, and then the 3 can't break out at all. Now I start looking at my variables. So 4 doesn't go into 5 nicely. So let's take a look at how many times can 4 go into 5? Well, 4 goes into 5. I can make one group of 4, and then there's one leftover piece that has to stay inside. For the y's, how many times can 4 go into 9? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 4 goes into 9 twice. And again, there is one leftover piece that has to stay inside the radical. Now, this is an even root. So whenever I have an even root, that means I should be checking my variables. So let's take a look at even, odd rule, okay? Now, if you notice, both of these started as odd. but the rule is even odd. So right away, I actually know that the rule isn't going to apply to either of these, right? Because I'm starting with odd values inside there, and it only applies if there's even powers inside there. So actually right away, I know this does not qualify, okay? I don't have to worry about that rule here. And last example for the day. So fifth root of 243. So fifth root, let's take a look at those. So fifth root, oh nice. So I was kind of nice in this one, and 243 is actually already on your list. The fifth root of 243 is just the number 3. So it's actually really nice when that happens. So that's just going to pop out as a 3. 5 goes into 10 exactly twice. And now notice that y to the 2. Notice that 2 is smaller than the 5. So 5 can't go into 2 at all. So whenever there's an exponent that is smaller than the index, there's no chance of it breaking free. So I don't even have to worry about that one. That's not going to break free, okay? It's just going to stay put right inside there. All right, so again, a lot of good stuff today, okay? A lot of good notes. So can you make sure, please, to write your summary, jot some things down that you want to make sure that you remember, okay? So jot all of that down and then come back ready to do your practice work.